Okay, if I can have your attention, we are happy to have Laila Andersson from LAST. She's did her PhD in the northern realms of Sweden at the Swedish Space Research Institute in Corona, and she came to LAST to work on the FAST mission to study earthly aurora, and has been involved in MMS and GOLD and other missions at LASP. Today she'll talk to us about an exciting new mission to Mars that is on its way, the MAVEN mission, and her involvement in that.
Thank you, and thank you for inviting me here. So, I will try to introduce you to the sister planets of Mars, sister planet of Earth, and say why Mars is interesting, especially if you're working on Earth. Then I will present the MAVEN mission briefly, first the science and then the mission itself. And then I will talk about the processes that we are interested in Mars, which is more or less the same processes we are interested here at Earth. And then I will end up with briefly talk about the siding springs and other missions which exist or will come to Mars soon. The Mars and Earth are two planets which we believe early on have similar history. We believe both were wet, both had internal dynamos, so both have magnetic field. Earth is closer to the Sun, roughly twice the size of Mars and 10 times as heavy as Mars. But today, the two planets' environment is quite different. The atmosphere at Mars, we have one, is roughly a tenth of, not a tenth, it's roughly 1% thickness compared to Earth's atmosphere. So the atmosphere is less than Earth today, now when we're dry. However, geology tells us that once upon a time, it was a lot of water on Mars. We see the rivers, etc. And we estimate it was maybe 10 meters of water on Mars. But today we don't see anything. So one of the big questions with Mars is where did it go? And especially since water usually inclines that life could start to grow. We are interested in when did the water disappear and could life have started at Mars? There are two ways for the water to go, either into the soil or out into space. We have found some water in the soil, but the amount we have seen with the rovers, etc., is not enough to explain all the formations, geology formation. So therefore the question comes, is the loss to space the major way that Mars lost its water? And can we today explain how it did, why it happened that way? So roughly 10 years ago, there were a group with Bruce Jakosky, which is PI of MAVEN, were sitting together and was scratching their heads. And for the Mars line, there used to be, MAVEN might be the last one, a scout mission line where a PI could propose a full mission with everything. And they said, we have a really good group, and we ended up mainly being CU, Berkeley, we working together with Lockheed Martin down here in Denver, Goddard as the management, and JPL for the attitude, and Goddard also with some instrumentation. Mainly those groups went together, wrote a proposal as a scout mission, and we were selected. We built the mission, and we launched it last fall. And what we saw that we could go after and understand was we want to understand how the atmosphere looks today. We want to understand how the loss of gas and atmosphere today happens. And with that information, we can start to extrapolate back and understand if the loss of water at Mars was via loss to space. One thing which is really interesting with MAVEN is roughly the time people think Mars lost its water was also when the dynamo disappeared. And therefore, one of the theory is that a dynamo is very important to keep the atmosphere and can explain why we lost the atmosphere of Mars. However, we have a little intriguing thing. If we fly behind Earth, Venus, and Mars today, the amount of particle leaving those planets, which is Earth as a dipole, Venus as an induced ionosphere, very thick ionosphere, and Mars with almost no magnetic field. There are some remnant magnetic field. All lost the atmosphere at roughly the same rate. So with the three different objects today having the same loss rate, what role do the magnetic field play for the planet, or have for the planet? Another thing which is interesting with Mars, as I mentioned, that today the dipole is gone, is that we have some remnants magnetic field as crustal fields, and they are especially in the southern poles. So we have small mini magnetospheres on the southern hemisphere, while in the upper one we don't have any magnetic field, so the solar wind will more become a draped magnetic field topology around the planet. Since we don't have too much magnetic field nor atmosphere, the standoff distance to the solar wind is very close. That means the solar wind particles can reach very far into the atmosphere. And we have a bow shock. We have something we call the MP boundary. A lot of missions which have flown here have had sparse number of instrumentation. So often it's been an ion detector, but no magnetometer, or a magnetometer and no ion. So this MP is almost equivalent to magnetopause, but we haven't had the instrument together to say that it is a magnetopause. And we know that this MP boundary do not stop all the protons from the solar wind. So the solar wind protons, a significant fraction can come into the upper atmosphere of Mars. We have a region where we see a very strong cutoff in the ionospheric density. So we have some kind of photoelectron density cutoff closer in. The gyro radius of the solar wind is also very strong. So therefore, Mars is almost comet-like to some extent, and especially close to these crustal fields is more magnetosphere-like. So it's a dualism which will be really interesting with MAVEN to try to detangle what is what is comet-like and what is magnetospheric-like. Here is simulations from a Japanese group in Nagoya about how one can see the atmosphere is stripped away from Mars. You see that it's very thin layer ionosphere, and the bulk ions is coming out here, while what we call the pickup ions is coming out here. a lot of the missions which have gone to Mars so far has mainly have high energy ion detectors, so they have very much focused on this part of the plasma. With MAVEN, we will be able to observe all the low density ions leaving the planet. So when we were putting together this mission, we had limited number of resources to fit into a scout mission, and we ended up with this MAVEN spacecraft, and we have 9 different sensors. We have SWIA, which is electrostatic analyzer for electrons, built at Berkeley. Its sister is SWIA, which is ion electrostatic analyzer built at Berkeley. I think both are from stereo design. Then we have the high energy electron and protons built at Berkeley, similar to the Themis instruments. And then we have another particle instrument here, static, from Berkeley, which is a mass resolving, and this is the one which will go for the lowest energies. We have magnetometer from Goddard, Langley probe, which I'm involved with. Then we have IUVS. IUVS is a little interesting, I think. A lot of you know probably about the GOLD mission, and we were trying to propose to fly a UVS, geostationary instrument at Earth, and we tried and tried and tried, and then we have the chance to propose a UV spectrometer for Mars. We proposed this one and built it and launched it, and we just have got selected for the GOLD. So it was meaning that GOLD were building first, and this would be a copy, but now it's the other way around. The GOLD instrument can be much more fancy than this one. This one is built at LASP. NGIPS is more or less the same instrument as flying on LADI and is built at Goddard. Then attached on the Langley probe, we have the EUV instrument, which is 3 diodes to look at the sun, which will be very interesting because we're going to have information of the sun at a different place than Earth. I think it's for the first time to continuously monitor the sun. Just to see how big the satellite we are. We choose this design because we can go down in altitude, and when it flies in the opposite direction, it's fairly aerostable for thick atmospheres. I think it was MRO bus, so and that bus was using aerobraking. We wanted to go down in altitude as much as possible, but on regular basis go into the solar wind. So more or less on every orbit we get a lot of solar wind data, and then we come down into the atmosphere. So we choose this orbit, which is roughly 4.5 hours long. And you see that we are in the solar wind, we can go in the sheath. We go into the day side, where we have a lot of plasma, and then the night side, which so far we just know the density is low, and this will be really interesting to go fly low altitude and get the information of the ionosphere there. We have an operation plan that each orbit is separated in 4 segments. Apoapsids, we are focused on looking at the planet as whole and try to do disk maps. On the sides, SVIA static, SVIA, it's static, and IUVS are sharing and deciding what prime science we're doing on the side. Then the major science objectives is here at periapsis, and then we have the outbound leg. We also choose a fairly high eccentric orbit because we wanted to process as much as possible, so our periapsis could cover as many magnetic local times and latitude as possible. We propose to do a 1 Earth year, not Mars year, Earth year. 2 Earth years is 1 Mars year. 1 Earth year mission. So our primary mission for MAVEN is just 1 year. And we cover most of the all local times and different regions during this time. So this will be the first time we really have a good cover of the full environment at Mars. We wanted to go as low as possible, so we're going to fly into different density corridors. So we don't have a fixed altitude, but we are going for periapsis at a certain density corridor. Normally, we're going to go down to 150 kilometers, and then we're going to go for 5 campaigns, go down to, say, 120 kilometers to get down to homopause, almost down to the F region. When I showed you the altitude here, I put the data points here is from the only altitude profile of the different species and temperature we have, which is the Viking lander back in the 70s. You see that we normally will go down to 150, and then during deep dip we'll come down and get the peak of CO2 plus and O2 plus. The atmosphere at these altitudes is fairly similar to Earth. One thing which is I personally find interesting is the O plus peaks above the exobase. So the main ionospheric part of the oxygen is very easy for plasma processes to heat them and erode the O plus. As long as we get O plus up here, the plasma processes could erode this very efficiently because we are above the collision region. We have a lot of radar or remote sensing information about the altitude profiles from the Marses on the MEX. MEX is a European Mars mission, and there we see a lot of fine structure in the ionosphere, cut-offs and erosion, and also in altitude, very dynamic, suggesting that we have waves in the ionosphere modulating the density. So it will be very interesting to now for the first time come in and fly frequently into 150 kilometers to describe how uniform or how much dynamics we have in the upper atmosphere of Mars. So how will we do this? The key question we have is how do Mars lost its water in the past? That is a really tricky thing because you need to have an understanding about the history of solar activity. You also need to understand how the different processes works for different conditions. not necessarily just today's conditions, but also other conditions. The history of solar activity, we can't go to Mars and measure. So we have to use existing solar models and use what other people are doing with investigating suns at other places in the galaxy and other suns, and see how their solar wind and EUV or UV changes. We can, which we are targeting at MAVEN, is to understand the different processes, how they are today and on what parameters they are working, so that we can, if we say that sputtering was much more prominent in the past, we can take that empirical correlation we see today and try to extrapolate back in time. The only thing that we can do directly by measurement by MAVEN is to look at different isotopes. So UVS will do D2H, and NGS will look at other isotopes, and with the isotopes we can a little better say what's going on in the atmosphere. So let's look at some of the processes which are equal of interest at Earth as Mars. The most simple way to lose atmosphere is just to heat up the neutrals or the ions and have them to be lost due to Jeans escape. Hydrogen is very light, so hydrogen is lost because it's warm enough and the gravity is low enough. However, the oxygen cannot be explained by Jeans escape because they are too heavy, so we need something else that helps the oxygen to leave. One of the interesting thing with oxygen is in the photochemistry, you have one of the reactions that provides two really energetic oxygens. And so we have a cold oxygen corona around the planet and then a hotter. And today we have not a good estimation of this hot oxygen corona, and if that could be good enough to explain the loss to space, or if we need to explain the loss to space by ion outflow directly from the ionosphere. So obviously for Jeans escape, one of the key instruments to target this is for the neutrals, the IUVS, which are doing full disk observation and limb scan and other things. Another process is the photochemical escape, and there is very much, do we understand the atmosphere it is today, or have we done something wrong? We also need to know what kind of energy input it is to the ionosphere to explain the densities and profiles we're observing. So we have the EUV observations, which is just 3 diodes to measure the EUV. And we're looking great forward. When we are coming to Mars, Mars will be on the other side of the sun, so we will have observations in EUV on the other side of the sun, while we have EUV observations from even other missions here at Earth, so we can get EUV information from 2 sides of the sun at the same time. So not only will it help for MAVEN, but our understanding how dynamic the sun is will be helped by these observations from MAVEN. One thing which, especially for the photochemical escape, which is very important, and I'm not biased at all. The most important measurement on MAVEN is to get the electron temperature. As I mentioned, the most we know about the altitude profiles, the detailed altitude profiles at Mars is from the Viking lander. It was Viking lander 1 and Viking lander 2. Viking lander 2, people usually say, it was a disturbed time, don't use that data. So we only have one, Viking lander 1. Here's the Viking lander 1 ion temperature profile, and this is the electron temperature profile. Electron profile is really hard to simulate. Hardly anyone is doing electron simulations, electron temperature simulations. So all the neutral atmosphere simulations, MHD simulations, plasma simulations is using this altitude profile on electron temperature. We do not know how accurate this one is. We don't know if it's the standard or extreme. And therefore I say electron temperature this might be the right one. If it's not, we might completely today model the Mars atmosphere wrong. No, I'm not working on the instrument measuring the electron temperature. So therefore we have 2 Langmuir probes on 7 meters stasers, and we are targeted to get a better understanding how the electron temperatures are at Mars. Most other measurement has to some degree been measured better or worse. So the electron temperature, the low energy ions, good isotopic measurement at low altitude, that is clear what we're lacking. But most of all, what we're lacking on measurement from Mars is that have all instrument on the one and the same mission. I said early on that one of the interesting things with Mars that it used to have a magnetic field. Now it's gone, we have some remnants. And we want to understand how we lose atmosphere. The magnetic field as such is not a process, but the magnetic topology and the change in the topology will allow or prevent plasma to leave the planet. For instance, Mars is rotating roughly in 24 hours as here at Earth. So we have those crustal fields which are rotating around. As they're rotating around, they will see the magnetic pulse, and we will have a connection. We have open and closing fields, and then they go behind to the darkness, and they can expand out, and maybe they can detach and get a plasma blob going back in the tail. So one of the key thing with MAVEN is we need to understand our magnetic field topology. So of course we have a magnetometer on board, but we also will use other kind of techniques like looking at the electron distributions, and this is from the MGS, where you can see if you are on a closed field line or if you are on open field line just based on the particle distribution. So we will use the particle distribution to tell the history of that magnetic field line. And of course, magnetic field is important when we interpret the particle distributions. But understanding how this dynamics, so we're much more dynamic magnetic field topology compared to Earth, since we have those crustal fields. It's more or less I'm visualizing, take a golf ball, have it smooth on the top side where we don't have any crustal fields, but on the bottom side we have grooves, but instead we have blobs coming out, and as it's rotating in the solar wind, you're going to have a lot of reconnection and other things going on. ion escape due to plasma process. Here we have, as I find, since I'm coming from Earth, I find the Mars community, they say as soon as you accelerate a particle or charged particle, they call it a pickup ion. So if you read a lot of Mars articles, everything is pickup acceleration. Coming from Earth, I would like to say bulk flow is when you have a temperature-wise very cold distribution, but it can have a significant drift. Ion outflow is usual that you start to have a very hot population and drift or a conic distribution. Pickup ions I want to associate with the particle which are neutral, which get ionized, and the energy they gain exactly at that time they are getting ionized. Any additional ionization will often be due to regular electric field and waves, etc. Also, looking at outflow, etc., if you want to understand what is controlling the outflow, it might be hard to identify it, and we will try on MAVEN. But for instance, once we get the particles in the solar wind, if it's an ion, it was immediately, it's mass loading and it will move it away from the planet. If it's a neutral, the neutral will hang there until it's ionized. Once it ionizes, the solar wind will bring it away from the planet. So taking a particle into the solar wind, the ultimate force or process that removes the particles from the planet is the solar wind. But it's not the limiting process for atmospheric loss. The bottleneck is most likely another process. But the solar wind is the end and have the most energy and finally removes it. So a lot with understanding the ion escape is to understand what part of this problem that you are focusing on.
Is this distinct from sputtering, or is sputtering part of this?
Yes, I have a slide coming out of sputtering, yeah. So at Earth, we have bulk flow, just heating going up. Outflow is usually in aurora regions where you have precipitating alveolar waves, parallel electric fields. This is simulations that I did, which I think is showing the complexity at Mars. I have a Capit code, it's a photochemistry in it, and I'm tracing ions. If we look down here, we see the blue region here. My simulation domain is going from plus 45 to noon to minus 45 at the equator. And it's very thin in altitude, but very long along the surface of Mars. So this is 5,000 kilometers, and this is just 150 kilometers. So the aspect ratio is not given the right. So what I'm doing, I prescribe a magnetic field. So I usually prescribe some kind of Drake magnetic field. Then I prescribe neutral ion densities, and then I derive the ions, and then I follow the ions based on magnetic and electric fields. I also prescribe ion heating via assuming at top of the domain I have ion cyclotron waves coming in. And what I can do is, for instance, allow a crustal field. I just put a dipole at the lower end of my simulation box to rotate across my simulation domain. And in this panel, you see altitude versus horizontal distance for O+, and this is for O2+ here. And I allow a crustal field rotate in, so the crustal field is roughly here and there. So this is from the same run, another run, and the third run. And the only difference between the 3 runs is Vallier et al. Saw that we can have a lot of neutral winds at fairly high altitudes. So I just put different altitude profiles based on these numbers. So I just made up neutral winds to see if we get any impact on the ions at Mars. And when I have this crustal field, due to the rotation of the planets in combination to how slowly or how long time it takes to recreate the O2+ ions. It takes roughly 2 hours. If you remove O2 ions, it takes roughly 2 hours to replenish that altitude profile. And therefore, when we disturb the ionosphere with the crustal field as it moves through, we can get quite different density profiles depending where you are and depending on which neutral. And this is what we on MAVEN have to start to detangle, understand the impact of did we have strong magnetic winds, did we have crustal fields, what the solar wind ionization rate, how much plasma wave heating do we have. So understanding how the ion outflow is taking place and where it's important will be a very complex procedure. So, last process I will mention is sputtering and impact erosion. Here we call sputtering is a constant low impact flux of particles. So, for instance, a SEP event, solar energetic protons that impact the upper atmosphere of the Mars would go into that category. While impact is more those sporadic thing, we have an asteroid going in and collide with the surface or survive the atmosphere and go in. The impact could be the reason that we lost the atmosphere. We don't know. However, building a mission to go and look at an impact event is really hard because we don't even know if it will happen in our lifetime. For the sputtering, we have, for instance, a SEPT observation, so we are measuring the SEPT particles as they come in, and we also can see if they are colliding in the atmosphere or if they're coming back up to the spacecraft. So depending on energy, if you go on energy of the particle which is coming in, and we look at which of them are coming back, we can say how far in they are colliding and where they deposit their energy into the atmosphere. Now, this impact. We actually have a little interesting things going on, and that is Comet Siding Springs. Roughly a year ago, I don't know if it was an amateur astronomer or whoever, saw a comet, a first-time retrograde comet. At the time when they initially saw it, they said it will collide with Mars. Now with time we have better and better orbit determination. We see that it will not collide with Mars. It will come to Mars around October. MAVEN is doing orbit insertion September 20 or 21, depending on which UT you want to use. So we will be there. But we are having our initial plan is that we have a 5-week getting ourselves in the right orbit and get all the instrument up and working. So in the middle of this transition phase, this one is coming. We are not the only one who's concerned of this. This is an observation from the Hubble in March this year. We know that the comet tail will impact the upper atmosphere of Mars. We are present assessing, both us and everyone else who's at Mars, to see if we think it's a risk and if we should do anything about it, and we still evaluate it. But this is more or less one of the lifetime impact events that, if we can, it will be wonderful to have measurement of the upper atmosphere before the encounter, and then after the dust tail of a comet has impacted the Mars atmosphere. I mentioned that there are other things at Mars. We have the rovers, MSL, the older Phoenix and the older rovers. We have Odyssey, MRO, and Mars Express. That is ESA missions, which NASA has a little collaboration with. MAVEN this year will come to Mars. One thing that NASA has is any mission that goes to Mars have to have the capability to be a relay to whatever they put on ground. So one of our instrument is Electra, which the first year will not do anything, because the first year we hope these assets is still working and are the relay satellites. If all of these 3 satellites die, MAVEN will step in and be the relay satellite. So even though that MAVEN have a normally 1-year mission, the plan is that the satellite will be much longer, and me as a scientist, I hope that the science measurement will continue. Yeah. This, I think this is a slide that headquarters showed to us. I don't even know if what this is. You know NASA's budget. Yeah. Yeah. The Mars exploration program, as you probably know, used to be firewalled from all other planetary missions, and they had their own budget. With that, they were planning a scout mission every 4th year, another mission, something bigger in between, and they were having collaboration with Europe with different missions. Now, Mars activities is not firewalled. They have to compete with other planetary missions, and the planetary budget is going down. So I know the next big mission, headquarters is trying to get 1 Mars mission and 1 to Europa, Jupiter's moon. I do not know if either of them is allowed with a NASA budget so far, so ignore this. And that's why I said MAVEN might be the last scout mission, because they can't guarantee the continuation with a scout line, especially now when they are merged with the planetary missions. So we have assets there now. MAVEN will not be the only one to reach Mars this September. I think it's 2 or 3 days later. We're going to have an Indian mission coming into orbit, MOM. I have not paid too much interest. It's a technology demonstration of the Indian to demonstrate that they can go to a planet, and they have taken instrument that they can build and put it on a spacecraft, so it's not a coherent science objective with that mission. Now they are launched, they are on the way, so we will learn more with them. They will be at a much bigger elliptical orbit than we. So in September this year, we're going to go in and fly around Mars. We have roughly 5 weeks, maybe 2 months of commission phase, and then we start our science phase. Roughly 6 months after the science phase start, all data will be publicly available, so anyone who's interested can analyze it. And I think this is the first mission that go to a planet that do not have any instrument looking at the surface. And it's one of the first missions going to a planet which have a really comprehensive upper atmosphere plasma package. So we will learn a lot from Mars, and comparing Mars with Earth is really looking as an interesting area. So I hope you are interested to think about Mars and maybe at some stage use some of the MAVEN data. Thank you.
Any questions?
How long will the comet tail encounter last?
It will last roughly 20 to 30 minutes. So it's fairly short. So we have an argument how to do it, how to not be impacted by it. It's shorter than I thought initially, but yeah. So the atmosphere, we're talking about a few hours to a few days before most of the atmosphere will be recovered.
How well do we know the crustal magnetism on Mars? Does it all come from in situ measurements of orbiting spacecraft? Or?
I don't know if the rovers have magnetometers on it, but the MGS had a really good magnetometer. They were in a dawn-dusk orbit, 300 kilometers. So they have done, based on that altitude, really good mapping of the surface magnetic field. We're going to go down to 150, so we will down a little fine adjustment to it. But a lot of study has compared the magnetic field topology with, for instance, emissions using the camera on MEX to see where that you get emissions at the crustal field. So we might have the auroral type of acceleration and emission at the crustal fields, and also the particle distribution supports the magnetic field topology based on the magnetometer.
So it does extend far enough into the atmosphere that you can see the particle?
Yeah. At some of the crustal fields are strong enough that they are impacting the bow shock.
Okay. With the electron temperature measurements, you were showing, the slide that you showed had some model simulations, if I understood what they were.
Yep.
And they had different heat fluxes, which I'm guessing are coming from the shock solar wind, how it's interacting with the ionosphere, or anyway, what my basic question is, what are the science questions that need to be resolved for the electron temperature?
Yeah, so when the temperature came back from the Viking landers, people said, can the atmosphere itself explain the temperature gradient? And I think everyone say that just looking at the atmosphere cannot explain the temperatures. We need an external driver to explain it. So that simulation was just that they apply some kind of heat flux on top of it to explain the observations. In my simulations, what I'm trying to do is I use plasma wave as the heater to the ionosphere and try to explain the energy into the upper atmosphere as that we have, for instance, ion cyclotron waves. What is interesting at Mars is if you look at the magnetic field strength, that's a solar wind, and at the exobase and the ionosphere, the magnetic field ratio is such that the proton cyclotron frequency in the solar wind ends up at the oxygen frequency at the ionosphere. So the regular solar wind flickering can be converted directly in heat or oxygen. At Earth, the magnetic field strength is so different, so the energy from the solar wind have to go multiple paths before we can get the energy into the upper ionosphere. So at Mars, it could be that we have just one big step to put solar wind energy into the upper ionosphere.
You mentioned that you need to the history of solar activity in order to understand where Mars's atmosphere went. Do you have an idea of where you're going to get those data?
I know there are people like one of the guys is working at CU Woods, but there are other astronomers who look at solar wind at different stars and see how strong they are. And then there are people who do modeling. I haven't read too much of them, but using that you can get upper bounds on how much stronger could the solar wind be, how much stronger could the UV light from a similar star be, so you can at least bound it.
Further questions? Let's thank Laila again.